about memprof, which is a memory profiler. So we're all Ruby developers here, and by now, I'm sure we all know a couple things about Ruby. One, Ruby's slow. And two, Ruby really loves eating RAM. So I'm curious, how many of you in here have either God or Aman set up to restart Ruby when it starts using a lot of RAM? All right, decent number of people. So that's pretty common in the Ruby world. And this talk is basically about what Ruby is doing with all that RAM that it's using. So to do that, let's start out, just take a look at what's going on inside the VM. And during this talk, I'm going to focus primarily on Ruby 1.8. So that's MRI 1.8.6 or 1.8.7. A lot of stuff also applies to 1.9 because the garbage collector in 1.9 hasn't changed significantly. But it does not apply as much to stuff like JRuby and Rubinius, which have much better garbage collectors. So this is what's happening with your memory. At the bottom, you can see all the physical RAM in your box. You have multiple processes running, and your operating system basically maps part of that physical memory into your process space. So if your process is Ruby, Ruby basically takes off that process heap several chunks of memory and carves those up into slots. And each of those slots basically represents a Ruby object. So this is what the slots look like, and the slots are either in use or not in use. And internally, Ruby, or MRI at least, has a linked list across several slots on the heap called a free list, and that basically points to every single slot that's free. And so when in your Ruby script you create a new object, basically the VM is going to go look at that free list and pull off the first object and use that as your new object. And so that goes on and happens basically as long as there's stuff on the free list. Eventually, you hit a condition where your free list is empty. And so the VM no longer has any empty slots to use for your new object, and so it has to run the garbage collector. Once the garbage collector runs, it basically goes through all the slots and tries to find ones that are not in use anymore and adds all those to the free list. And now that there's objects on the free list, it can continue as normal. There's also another condition where maybe all the slots were in use and it wasn't able to find any garbage, and the free list is still empty. And so in this case, it has to go ahead and allocate a whole bunch of new slots, and it adds all those slots to the free list, and then again continues on as normal. So I said this talk is about the RAM usage, but it turns out the Ruby's GC, especially in MRI's case, is also one of the big reasons it's so slow. And so addressing these concerns can actually help in both aspects. So why is this so slow? It's basically because MRI, again, has a conservative, stop the world, mark and sweep garbage collector. So what does this mean? Conservative. Conservative basically means that the Ruby VM will hand out raw pointers to Ruby objects to C extensions and anybody else who asks for it. Stop the world means that when the garbage collector is running, nothing else can happen. So basically, while your garbage collector is running, none of your Ruby code is running. And mark and sweep. Mark and sweep is basically a very simple garbage collecting algorithm, and it has two phases. The first is the mark phase, where it basically goes and tries to find every single object that's in use and puts a mark bit on it. And then once it's marked everything that's in use, it'll traverse each of those slots, and if the mark bit is not set, it'll free that slot. So these three design decisions have some effects on what happens. Basically, the fact that the GC is conservative makes it really hard to implement better garbage collecting algorithms. So we're basically stuck with mark and sweep for now, and this is because the raw pointers that are handed out make it very hard for the VM to know what's going on with objects and what objects are still in use. Stop the world means that nothing else can happen, and this is particularly bad because most of us write web apps. And this means that if during a request the garbage collector starts running, that means that basically adds to the amount of time that the user has to wait for a response. And so if your garbage collector is taking say, 100th of a second every time it's run, and it gets invoked once or twice during a request, that's 200 milliseconds that the user is waiting longer than they had to. And mark and sweep is a fairly naive algorithm, and the problem is basically it doesn't scale up as you add more and more objects to your heap, because it has to basically touch each and every one of those objects every single time the garbage collector is run. So this basically means that the more objects you have, the longer your GC is going to take. The longer your GC takes, the less time you're actually running Ruby code. And so what this means is if you can reduce the number of objects in your MRI processes, you end up with better performance. So there's a couple things you can do to improve performance. One is remove unnecessary object allocations. Object allocations are not free. Nothing is really free when it comes to computers. Everything is sort of a trade-off. It's important not to take this too far, but you can definitely profile your applications and find hotspots where you're allocating a lot of objects and you might not even know. The big thing is to avoid leaked references. So this could be considered memory leak, although it's not technically a memory leak. It's a leaked reference. So what's going on here is basically you created an object and you don't need it anymore, but you're still holding a reference to it. And the way the garbage collector works is as long as any object is referenced, it's going to assume that object is in use. And so it's going to not garbage collect it. So let's look at this example. Here's an instance of class A. It has an array instance variable. And in that array, it's holding a bunch of instances of class B, each of which has their own array and sub-objects, and so on and so forth. And so what this means is as long as there's a reference somewhere to that very first object on the top, none of these objects in this image can be freed. And it's really easy in Ruby to inadvertently hold references to objects that you might not need anymore. And since those objects hold references to other objects, so on and so forth, you can end up with a lot of memory bloat really easily. So I'm going to basically talk about a bunch of useful tools that you can use to debug problems like this and try to reduce the number of objects and thus reduce the time spent in GC and improve your performance. The first is a method on object space called each object. And it basically lets you iterate over every single object that is currently live inside the VM. So here's a really simple loop. I just create a hash and basically tabulate how many objects of each class exist. And this will, once you print it out, sort it and print it out, you'll see something like this. And this is a really simple way to get a sense of what's going on inside the VM. And here you can see there's a lot of strings, and you'll notice, other things. A really easy way to leak references in Ruby is through procs, because procs are closures, and they basically reference all the local variables defined around them. And so you might see in here a lot of procs, or you might notice, you could do this over time, and you might notice the number of classes is going up, and maybe you're leaking classes or something like that. In Ruby 1.9, this is made even easier. There's a new method on object space called countObjects. The big problem with this method is since you're doing this in Ruby, you're actually creating objects. So it's not perfect. The Ruby 1.9 method makes it a little bit easier. It'll try to reduce the number of objects that are created while it's doing all the tabulation. So this is really simple. You can do this without any patches, without anything. You can just pull up IRB and try this, or maybe add a special URL into your Rack or Rails application to print this out. The next tool is gdb.rb. So this is something I wrote a few months ago. It's basically a bunch of hooks for GDB for the REE VM. And what this lets you do is basically attach to any running REE process and inspect the Ruby heap. So you can get a lot of information out. For instance, on the right, you'll see I typed in, it might be a little hard to see, but I typed in Ruby objects, and it basically tells me how many objects there are, how many slots, how many of those slots are free, and then a breakdown by type of those objects. So you'll notice in this one, there's 83% of the heap is nodes. And nodes are a special type of object in Ruby that actually represent the code itself. And it's one of the reasons that Ruby is so dynamic. You can add and remove methods and classes, and they're all represented on the Ruby heap just like any other object. And so once you delete a method or undefine a constant, the garbage collector will notice that it's no longer being referenced and can get rid of it. There's a bunch of other stuff in GDB.RB. One thing to note is that it only works on Linux. And the way it works actually is it's a bunch of Python code because GDB 7 allows you to script out commands using Python. So it's a bunch of Python code that understands how the Ruby VM works and lets you debug Ruby. So I've used this in a number of applications to fix problems. One was in a plugin for Rails called Rails Warden, which is an authentication plugin. And there was an issue where basically for every request it was leaking every single middleware. So this was actually on a production server where there had been exactly 4,124 requests that had came in. And I was able to attach to the process in production and run this command and see exactly what was going on. And we knew where to start looking and we were able to fix the problem. Similarly, there were a bunch of leaks in God for a really long time. And they were particularly hard to track down. It turned out there were actually 5 different leaks in God. And using GDB.RB, we were able to attach to a bunch of processes in different environments and basically notice what was leaking and then try to find out why it was leaking. Another useful command or set of commands to GDB.RB let you print out arrays, hashes, and strings by length. And so you'll notice over here there's several arrays that had 94,000 elements in them. And these were basically arrays that were growing infinitely large and holding references to a bunch of objects and essentially leaking references. So another useful tool is a tool called Bleakhouse. So Bleakhouse basically installs a custom patched version of Ruby. And the advantage of Bleakhouse over some of these other tools is it'll tell you not only what is leaking, but also where the leak is happening, which is really useful. So you might know that this certain class is leaking, but it can be really tedious to go through all the gems and all the libraries you're pulling in, as well as all your application code, to try to figure out where that leak is actually happening. The nice thing about Bleakhouse, it'll give you output that looks something like this, and basically it'll break down for every file and line number and class name the number of objects that are allocated on that file and line. So this is pretty useful. The downside of this is that when you install this gem, it actually installs a custom patch of Ruby. So it's not, you're no longer using your own Ruby, you have to use Ruby Bleakhouse. And this means that you have to go ahead and reinstall all your gems, which can be a little painful sometimes. So this Bleakhouse was pretty useful. I used it on a particular project and found out a bunch of information. So I saw something like this. It gave me a file and line number and told me I had several 100,000 strings. The problem was I still had no idea what was going on. So I knew the exact line and knew there were strings, but without knowledge of what was actually inside those strings, it was really hard for me to tell where they were coming from. So I wrote a really simple patch that was based on the Bleakhouse code. It ended up being about 300 lines of C code. And instead of just printing out the file and line number, I printed out a bunch of other information about the Ruby objects themselves. So I chose a really simple text-based output format. So you can see on the left there's the memory address. It'll give you the file and line, the type, and then, for instance, for strings, you'll see the length and the value. For classes, you'll see the name of the class and the superclass, and so on and so forth. So this would dump out in this format, and it was actually not too hard to analyze. So I could just use a whole bunch of Unix utilities. Using WC, you can see there's about 1.5 million objects, and I knew the problem was in this memcache library. So again, I did some awk and grep and sort and basically picked out the file and line that had the most number of objects in it. And Bleakhouse had already told me this, so I was trying to dig in deeper. So then I broke it down by type, and again, I knew strings were the problem, but I still didn't know what was inside these strings. But since I actually had this information now, I could grep out all the strings and then do a count and sort on the actual contents of the string. And what turned out in this case was actually I was using the SQL database library and as a caching mechanism, basically storing instances of SQL models into memcache. And the problem was one of the instance variables on each of the model instances contained all the types for all the fields. And so basically, every time I would pull stuff out of memcache, I would end up creating a whole bunch of these strings that were basically varchar 255, tinyint1, and so on. And by getting rid of this instance variable, all these strings went away, and the number of objects went down drastically, and the time spent in GC went down, and I was able to serve more requests per second. So this brings us to the tool that this talk is primarily about, a tool called memprof. And memprof was basically something that was developed after using all these other tools and basically seeing a need for something more, something better. So the goals for memprof were basically, one, it had to be easy to use. A lot of these other tools had a lot of overhead where you had to first patch your VM or reinstall your gems, stuff like that. And so the goal was none of that stuff would be required. You would just be able to install a gem, require it, and start using it. I wanted it to be very detailed. So I started out with object space, which gave me only type information. Then Bleak House gave me file information. And then custom patches gave me contents of those objects. But the big thing that was still missing was information about the references between the objects. And so if you know that a certain object is leaking, it's really helpful to find out what is referencing it so you can find out the root cause of why that object's being leaked. And then finally, I wanted a really easy way to analyze all this data because there was a lot of data. So I started out originally with a simple text-based format, which got a little cumbersome because I had to constantly go back and look and see what field number I was interested in, and then write a huge long awk and grep script to try to pull out the data I wanted. So I figured the easiest thing to do would be to use JSON, and that way I could dump out a lot of information and still analyze it using whatever scripts I wanted or various databases that supported JSON. So memprof is on GitHub and available as a Ruby gem. You can basically gem install it and start using it. It's under active development. Currently, it only works on 64-bit Intel CPUs. It supports both Linux and OS X. For best results, I definitely recommend using an RVM installed Ruby. You can use any Ruby 1.8, so that includes Ruby 1.86, 1.87, or REE. We're currently working on both Ruby 1.9 support and 32-bit CPU support. So the way that this works under the hood, it actually does some crazy binary rewriting. So as your VM is running, it'll go and find specific call sites to internal functions inside the VM and rewrite them to call memprof functions instead. And this basically lets memprof know anytime you're either allocating an object, freeing an object, or doing other stuff related to garbage collection. It uses a bunch of C libraries to basically access debugging symbols inside the Ruby binary, and uses libagile, which is an awesome JSON library written in C. There's a bunch of blog posts that we've been doing over the past few months detailing all the lower level stuff that goes into making memprof possible. They're all available on timetobleed.com if you're interested in learning about assembly and how the compiler and linker works. It's pretty interesting stuff. So memprof has a bunch of features that I'm going to cover. The first is memprof.track. So this is very similar to Bleak House, but it actually only reports for a given block of code, which is pretty useful. One of the problems with Bleak House is that you'll get information about every single object, and so the technique you end up using is basically you run it several times and then subtract dumps from each other to try to figure out what changed. Memprof.track just takes a block, and for that block, it'll report in the exact same format that Bleak House does. So here you can see I'm creating 100 strings, 100 floats, and 100 modules, and it'll tell me the file line and the type that was created, along with the number, which is 100 in all these cases. There's also a wrapper around this, memprof middleware, and so you can load this middleware into your application, and for every request, it'll basically dump out to std out or std error a little report like this. You probably want to run this in production mode because in development mode, Rails in particular will create a lot of garbage since it does source code reloading. So if you run this in dev mode, you'll see a lot of output and it won't really be as meaningful as in production mode. The next feature is memprof.dump. And so memprof.dump on the top right, you can see again, takes a block. And basically for all the objects that are created inside that block, it'll dump out a bunch of details as JSON. So I'm going to show a couple examples that'll give you some insight into how the VM works and how the VM stores a bunch of commonly used objects. So first up is strings. You'll see a JSON dump, something like this. And so the first thing is the memory address of the object. You'll see, again, the file and line where the object was created. In this case, it's a string. So you'll see the type is string, and then it has a pointer to the memory address for the class that represents this string. So in this case, the class is string, but maybe you subclass string, and then it would point to the subclass of string that you used. And of course, strings have a length and data, and so it'll dump out the data inside that string and its length. You can see I concatenated hello and world, so the string is hello world. So similarly, arrays. I'm going to dump out this simple array that has 4 elements. You'll notice here that the first 2 elements, 1 and the symbol b, are stored directly in the array. And that's because these are something that's known as immediates. And whereas the second 2 objects, the float and the string, are not actually stored in the array, the memory addresses of those objects are stored in the array. Similarly, for hashes, you'll see there's a data element that basically stores key value pairs. And again, you'll notice that the symbol and the fixed num are stored directly in there, whereas the other 2 are pointers to where they actually live. Again, the nice thing about JSON here you can see is that it's really easy to use embedded objects to represent exactly what's going on. And you'll notice here that this hash does not have default proc, so the default is null, whereas if you had a default proc on this hash, that would again be a pointer to a proc object somewhere else. And finally, classes. So here's a really simple class. It has a class variable, a constant, and 1 method. And you'll see that it creates an object of type class that has a name. It has a superclass, which makes sense. You'll notice that there's an instance variable table. And so actually, it's interesting, in the MRI VM, the instance variable table holds not only instance variables, but also constants and class variables. They're all on the same table. And the naming rules allow them to all reuse the same table because class variables have to have the double @ sign, constants have to be capitalized. And finally, there's a method table that represents, again, method objects. These are full-blown objects like any other object inside the VM. So when you go to call this method, if you call the method, it would look up the method table, find that object, execute it. If you called another method, for instance, the method foobar, and it wasn't in the method table, then it would go look up the super, go to that object, look in its method table, and so on and so forth until it found it, or it would eventually return no method error. So the next feature is a similar feature, but instead of just dumping out specific objects, it dumps out every single object. So it's called dump all, and you basically give it a file name, and it will go through every single object defined inside the VM that's currently alive and dump it out to the file name that you specified, 1 per line. And the cool thing about this is, since it's all JSON and it's just in one big file, this file actually ends up being pretty big. On a Rails application, it will probably be about 250 megs of JSON. But it's all just JSON, and it's 1 per line, so you can do a whole bunch of analysis on it, and you can use a variety of different tools. So I've used JSOC and grep, which have been pretty cool. I use Mongo pretty extensively. The cool thing about Mongo is that you can add indexes on any field, including embedded fields. I've written custom Ruby scripts, and most recently I've written a bunch of C and C++ code to try to do some graph analysis on the object graph. That's one of the features that I'm working on for memprof right now, and the cool thing about that is you can run a bunch of graph algorithms on the object graph and basically find sort of hotspots of where you're allocating a bunch of objects that point to each other. So finally, one of the features of memprof is a web-based service called memprof.com, which is a web-based heap visualizer and leak analyzer. So this is basically takes that dump from memprof.dumpAll and loads it into MongoDB, applies a bunch of indexes, and then creates a nice little web UI to sort of visualize all the objects inside your heap. So I'm just going to show off a bunch of features and then go through an example where I try to find a memory leak. So you can use this to explore class hierarchies. So here you can see the I/O class hierarchy. TCP socket inherits from IP socket, basic socket, I/O. On the right are two dumps from a Rails application. So you can see Rails subclasses string in a bunch of ways. And on the bottom, you can see the Rails 3 controller hierarchy. So all the controllers inherit from base, which inherits from action controller metal. It's also really useful for finding large objects. Again, I mentioned in the past, gdb.rb lets you find really large arrays or hashes. So here's an example where I found an array in a production Rails application that had 4,000 elements in it, and I traced it back to the code on the right, which is a little hard to read and it doesn't really make sense, but it ends up creating this huge array that's basically a whole bunch of two-letter strings. So the string AA, AB, AC, and so on and so forth. A couple other things you can do. You can group by file. And so on the left you'll see this is a bundler. And so you can basically I'm breaking down number of objects per file, and then in a file you can break down by type, and then by type you can break down by class, and then go all the way down to the line number. And so you'll see in this case there were about 46,000 instances of bundler mode specification. And so on the right, then I started to try to find out what was referencing these. And so you could basically start expanding out objects and follow references back to the root nodes that are holding the references. So you'll notice in here that there was a bunch of gem versions that were being referenced by the remote specifications that ultimately led back to the bundler installer. I mentioned that nodes are stored on the root heap like any other object. What this means is that you can actually, using this heap dump, reconstruct the code, which is really interesting because you can see the generated code for methods that might have been created using metaprogramming or other techniques. There's a lot of interesting stuff in Ruby's standard library that I ran into. On the top left there, you'll see a really nasty loop inside singleton.rb that's doing a while something sleep nil. So that's pretty useful. You can also get a lot of information about open file descriptors and shared libraries. So you can see all the shared libraries that are being pulled in, or take a look at open sockets and then actually see the underlying file descriptor that's associated with that socket. So on the right, you'll see that that TCP socket instance is actually connected to Google's HTTP port. You can also group objects by time, which is pretty useful. So you might notice that you're creating a lot of objects that were pretty young, or you might notice that as soon as your process booted up, it allocated a bunch of objects. You can dive into what those are and try to get rid of some of them. You can see global variables. You can do a whole bunch of filtering by type. So here, these are all the procs. On the left, on the right are a whole bunch of stack frames that were defined. So those are all the method calls that were currently being made when this process was snapshotted. And on the bottom, you'll see a proc. And one of the cool things about proc is you can hover over any of the local variables that are defined inside that proc and see the values of them. So that's pretty useful for debugging. So basically, I'm gonna try to show off how I would use this to debug something. So we're using Rails 3 in production and have been for a while. It's actually worked out pretty well. But one of the things we noticed pretty fast was in dev mode, it was leaking pretty heavily. So basically, after 10 or 15 requests, we would notice that, I would notice at least that my fan would start spinning up, and I pulled up Activity Monitor and noticed it was using anywhere from half a gig to a gig of RAM. So I decided to try to use memprof to find this problem. So the way I do this is basically gem install memprof and then require memprof/signal. Boot up my Rails application, send it a bunch of requests so it starts leaking, and then basically run the memprof command, give it the PID of the Rails application to dump out the heap. And what this does is basically it calls memprof.dumpAll, writes it to a temporary file, uploads that file to memprof.com, and then gives you a link so you can go start looking around in that heap dump. So I'm going to pull this up just so we can walk through it. So here's a very simple Rails 3 beta application. Oh, I can't see it. Let me mirror displays really quickly. All right, so there's a bunch of information here. You can see it was using about 97 megs of RAM, and there were 400,000 objects. There's classes, modules, a whole bunch of stuff. So basically what I did was I clicked on a whole bunch of these links and tried to look for stuff that looked weird. And I ended up clicking on duplicate classes by name and noticed that there were 51 copies of my controller. And 51 happened to be the exact number of requests I made to this application. So I know something's going on here. I can expand this, and sure enough, all these instances are in my test controller inside my application. So I want to try to figure out what's going on here. And you'll notice that, again, I said that this is built on top of Mongo. So up here is the Mongo query. So I'm basically pulling out all the classes and grouping them by name. And you can see there's 2,400 classes. So test controller, I want to see what's going on with test controller. Again, I run a query that basically says, give me all the classes that are named test controller. There are 51 of these. So now I want to try to figure out what's actually holding a reference to these classes. Why are they leaking? So I can click on one of them. You'll see a bunch of information about it. You know, all the modules that are pulled in. Down here you'll see the instance variables and the methods that are defined on it. You can click on a method and actually see the code behind that method. But what we're interested in are the references to this controller that are causing it to leak. So we can try to look at all the references, and sure enough, the first two are, again, two hashes that have exactly 51 elements in them. So that's pretty suspicious. Let's click on one of these. So this happens to be a hash that's defined on line 3 of localized cache inside abstract controller. And sure enough, it's using the controller object as the hash key, and then storing, looks like it's storing some localization information about that controller. And the problem here is basically, since we're in dev mode and the code is being reloaded every request there's a new test controller class that's created. And since it's using that class object itself as the hash key, it ends up creating multiple entries and leaking those references. So here's one, localized cache line 3, and then similarly, there's another one in metal.rb on line 74. And so it basically, this interface lets you dive into not only details about the objects, but also the references. And it's a really easy way, once you know there's a leak taking place, to try to figure out where it's coming from. All right, so that's basically what I'm showing here. And like I mentioned, basically, there was a bunch of caching going on inside Rails to try to speed things up, but in dev mode, it ends up leaking references to all the controllers that are being reloaded using source code reloading. So the patch was pretty simple. Instead of using the class object itself as a hash key, you just use the class's name as the key. And so even though a new version of test controller gets loaded, you just use the string test controller as the hash key. And so it overwrites the old entry, and those leaked references end up going away. So that's basically memprof. So far, we've focused mostly on memory profiling. We're currently working on a couple more features. These are currently under development. One that I'm pretty excited about that I'm just going to talk about briefly is a tracing framework that we've been working on. So this is sort of a hybrid between profiling and memory debugging. And the way this works is it's basically a middleware that you can use in your Rack or Rails applications that will, per request, record a bunch of information out. So the information that we're currently recording is the total time for the request, a bunch of basic information about what Rails controller in action, what the requests look like. And then we hook into, using the same techniques that we use to hook into the Ruby VM, a bunch of common libraries. So one of those libraries is MySQL, for instance. And so at a C level with really low overhead, we're able to track both the number of queries and the time spent executing MySQL queries, which is kind of interesting. The more interesting stuff is the other hooks we have into the GC and object creation itself. So in this case, you'll notice that during this request, which took 4.3 seconds, 2.0 seconds of that was actually spent in the garbage collector, and the GC was actually invoked 8 times. So information like this is pretty useful, and the idea is basically that once you end up with a bunch of data, you can start aggregating it on the Rails controller in action and try to figure out what actions are spending a lot of time in GC, and then try to go optimize those. So in addition to GC, we also record the number of objects created and a breakdown of where those objects, what types of objects were created. So you'll notice this one was particularly heavy. It created almost 4 million objects, which is one of the reasons that garbage collection ended up happening 8 times. And then you'll see a breakdown. As you'd expect, there's a lot of strings because most Rails applications are basically rendering templates and creating strings. There's a lot of arrays and hashes. A surprising number of matches in here, so this probably means that a lot of regexes were being run and creating match objects. There were about 1,100 object instances, so these are instances of custom classes that are not core classes, and then about 1 million method calls. And this shows up under the none category because every time you call a method, internally the VM will create a temporary object that holds all the local variables. And then as soon as the method call is done, it clears out that object. And so by the time we dump out the information, it looks like it's not really an object. But it's a good measure of how many method calls were being made during that request. So that's basically it. Any questions? The question was about if I've looked at JSON parsing versus YAML parsing.
Because the YAML2 parsers use JSON as a subset.
Okay, and specifically about YAML2 because it uses JSON. I have not. I decided to go with JSON primarily because I wanted to use MongoDB, and so I didn't actually consider any other formats. And JSON is simple enough, and there's so many. One of the big reasons was also because I'm doing all this in C, and libyagile is a really nice JSON library that lets you both generate and parse C.
Right. So the YAML2 parsers parse JSON.
Oh, interesting. Okay.
Because it's a subset of YAML2, and the libyaml library is on its way to supporting that. There's a Haskell implementation as well.
Okay, so yeah, so libyaml apparently supports JSON parsing. I did not know that. I'll check that out.
The next implementation.
Okay, cool. Back here. So the question is about binary compatibility and if you have to rebuild and how often you'd have to rebuild the gem given different Ruby implementations. The thing is, if anytime you install a new Ruby VM, you're going to end up having to reinstall all your gems anyway. And so basically, once you install it, it's going to work for as long as the gem is installed. This technique actually ended up being a lot easier than what we were doing before, which is patching the VM itself. And we'd have to maintain 5 or 6 different sets of patches for every single revision of Ruby, Whereas using this technique, it's a little bit more like duck typing or monkey patching. We basically expect certain methods exist at the C level, and we don't actually care where in the code they were defined as long as they exist. And so it's a lot easier. We just have one code base that works with all 1.8 releases and already has partial support for 1.9.
It essentially works like a linker, right?
Yeah, it basically swaps out the linker's entries for where those functions are and calls our functions instead. The question was if we're working with the Rubinius guys. I have not looked very deeply into Rubinius. I know they have a bunch of tools built in, and that's one of the really cool things about that project, is that they already have their own profiler, and they have much better GC and a bunch of instrumentation into that GC. The thing with these techniques is that they're specific to the VM, and so they basically, we'd have to go in and take a look at how the VM works and write a bunch of code that hooks into the VM specifically. And I'm not sure how that would work because they are using a lot of advanced VM techniques using LLVM, et cetera. But it might be possible.
Rubinius already supports various things like PERT as output format from the full-speed profiler and all that stuff. So you should be able to really easily get JSON straight out of it without having to.
That's awesome, yeah. Apparently, Rubinius already supports output formats for its instrumentation. That's something we definitely looked at. The nice thing about JSON is that you can express all the information that's inside the VM. And so we could write something for JRuby or Rubinius that dumps out JSON representing what's going on and then load that up into the memprof interface and try to visualize it in a similar manner. Yeah, the suggestion was to try to auto-discover sort of magic numbers. For instance, the number 51 showed up a lot because that was the number of requests that came in. That's definitely something I've considered. It's kind of hard when you have a really large data set, but it might be cool to search, for instance, if you know that you put in a certain number of requests to try to find where that number occurs. The question was about sort of the future of garbage collection inside the Ruby VM. It's definitely one of the areas of focus as far as 1.9 is concerned, and they've already made a bunch of progress. So one of the biggest things in 1.9, 1.9.2 specifically, that's going to change is that the source code, the nodes, are no longer stored on the heap. They're stored on a separate heap that's not garbage collected as often. And that's going to be a big win for everybody because most of the objects inside any application, any big Ruby application, will be nodes. On that one dump I showed, it was about 83%. And if you get rid of 83% of the objects, the time spent in GC is going to be much, much lower. The bigger problem, however, is that we're sort of stuck with mark and sweep for the time being. And that, again, goes back to the fact that the garbage collector is conservative and hands out raw pointers to all the C extensions. And so it's hard for the VM to know which objects are in use or not in use. And so it has to assume the worst case and basically assume that if it sees a pointer somewhere that looks like a pointer to the Ruby object, it actually is a Ruby object that's being used. And so it really limits what you can do, and it makes implementing a lot of the much better GC algorithms much harder.
Yeah, Koichi Sasada, the author of the 1.9 VM, actually told me that that's the reason he can't change the garbage collector is because there are too many C extensions that rely on that behavior. There's no way it would be a forklift upgrade for everybody.
Right. I mean, you could change it, but the problem would be most C extensions would break. And so it's sort of a trade-off. And Rubinius has actually done a really good job where they've gotten rid of a lot of the macros that allow raw pointer access, but still expose most of the C API. And so with minor changes, you can get most C extensions up and running, and they're able to sort of get best of both worlds. And maybe something like that could be brought over to the Ruby 1.8 and 1.9 VMs eventually. Anyone else?
When's the memprof.com service go live?
It's currently in sort of a beta phase. We put it out there. It's if you want to use it, you can definitely use it right now. By default, all dumps that you upload are visible to the public. If you send one of us a message or an email or tweet at us, we can enable the beta flag on your account, and then anything you upload will no longer be public. We definitely encourage you to use it if you have memory problems, and it helps us to try to see common memory issues out in the wild and work on solutions for them and try to make the UI better to make it more intuitive. All right, thanks a lot.